we'll see.
Okay, folks, probably time for us to go ahead and get started, but I think we've got a pretty relaxed schedule for the talks today. So just to remind everybody, I've got my, I should grab them, the handy dandy grading rubrics for the presentations, just so that everyone's on the same page. This is what they look like. If you want to see it, it's on Canvas as well. So the grading for this is based on comprehension, correctness, and clarity, 5% each. So my interpretation is comprehension is your comprehension of the quantum field theory aspect of your topic. So that's 5% for correctly describing the quantum field theory components of your topic, 5% for clarity of the presentation, including both verbal clarity and written clarity or slide clarity, and then just correctness of your physics about whatever topic you're presenting on. I intend for this to go the same way it did last semester. I think things were pretty laid back. I was very happy with the presentations. I don't think there were any issues as far as poor presentations or problems with the grading there. Any questions on how this is going to get translated to Canvas? Okay. Next thing is topics. So we have 9 people officially registered for the class. I think I had 3 people mention to me thus far that they are not prepared to present today. In some cases, people wanted to set up a one-on-one or set up an individual time slot, let's say by the end of this week, because they're not ready today, but a couple of days might do it. I think in some cases it's going to have to happen sometime over the summer. So at the moment, to my knowledge, we will have Muhammad Ali, Joe Botter, Nick Baldonado, Danupa Batudagara, and Antonio presenting. Jacob, I think, is also presenting today. The 3 who've spoken to me are Jeremy, Masood, and Hassan. So I believe that we will have 6 presentations today instead of 9. So that potentially saves us an hour and a half on the schedule that was originally planned. So that's why I wasn't too worried about us getting started a half an hour or so late. We can also choose whether we want to take a little bit longer time for lunch, so because 30 minutes is pretty rushed, or if we just want to get it out of the way and be done sooner. Do you guys who are here in the room have an opinion on that?
I would prefer faster, but I don't know if you guys.
No, that's how I brought like peanut butter and jelly sandwich. So I can just keep on going and watch.
The faster it is, the sooner I get to eat.
Okay, Antonio's on a hunger strike until the presentations are finished. Yeah, that's fine with me, but I don't have any strong feelings either way. So if you guys have any boundary conditions or other constraints.
But it's not like it's 30 minutes. It could be 35.
Yeah, so I mean, part of the grading for the presentation is on the clarity and the timing. So I'll still, ask you to try and aim for 25 minutes. But if there's a good discussion that happens afterwards, I'm not going to cut it off at 5 minutes if we're not pressed for time. Okay. So that's sort of the plan. We had some natural order of speakers that was suggested, but that's kind of blown out of the water now. It could still be nice if Nick presents before Joe. That would at least be a natural segue. Muhammad has nicely volunteered to go first, and we can kind of take it from there.
Where should I go? Do you think I should go?
I think that can go in any order. I was going to ask if Danupa had anything in particular, since Danupa is joining remotely. Do you have a time slot that you would prefer to speak at, Danupa?
No, I'm free all day.
Okay, then maybe we'll just take it one at a time. We can start with Muhammad Ali's talk, and then whoever feels inspired to go next can go next. So any questions before we dive on in? Okay, so we've, I believe, downloaded all the relevant presentation materials. So Muhammad, feel free to present from here. He asked for a couple of minutes to show a video from his YouTube channel.
To thank you about for
the lights are over here, so I can turn this off. Should I turn off all lights or just half lights?
I can see fine. I don't know all of these.
Half lights. It depends on what your color scheme is. This is probably okay for most. You want both off?
Yeah.
Okay.
No.
Oh, this is okay? Okay.
Hello, good morning, everybody. I need to show you this video, and I need to. Can you hear me online?
I think all the audio
but I cannot see the
microphone here.
Okay. Is the no?
No. Can you lower the camera a little bit?
We might need to adjust the audio. So try it, and if the audio is not working, we might not coming from the computer there, we might need to play it on my computer if that's easier.
Again, please.
Try it here, and if the audio doesn't work, we can play it on my computer. Okay, it's working.
Play it here.
Okay, should be good then. Oh, can you pause 1 second? Sorry. Oh my gosh.
What about?
We just want to share screen on the Zoom, so.
Yeah.
Okay.
This is better.
Okay, there we go. Please.
Excellent.
Okay, so thank you guys very much. I'm really happy to have you here. So this is Physics 554. I think all of you. So if you are talking about a field, you need to specify what the elements are. Yeah, so it comes down specifically when it comes to So another way to say this is that when I have that matrix on, let's see, I have 8 participants online, 2 of which are me, and I have 3 people in the group. So that's how I got booked the class. Wow, that's very fast.
Lots of action.
We covered a lot of ground, didn't we?
So I'm happy to leave it here. Thank you guys very much for sticking around for this. I will post the video online for anybody who is not able to watch this. You guys have, hello everybody. It's good to have you back. This video is intended to be an optional video before the official start of class on Monday. I wanted to spend some time reviewing the main messages and problems we looked at in Physics 554 last semester. But I collect the overall powers here. I have some j equals 0 to infinity. Morning, folks. Okay, good morning, folks. I've got a few minutes past, so we should go ahead and get started. We've got a full hour today. The topic is very interesting and important about the fine and the hyperfine structure of hydrogen. The assignment will become available, and I will be available on Zoom on that special room for the 2-hour block. Thank you. No problem. All right, thank you guys. It's been a hell of a semester. I appreciate you guys sticking with me. So, welcome everybody for the first semester of quantum field theory, Physics 691. I think everybody here in the room I know already. Everybody online I also know already. Is characterized by 2 eigenvectors. Exponential. Since this is a diagonal matrix, exponential of this element, exponential of that element is the same thing as exponential of the. Okay, folks, I've got 2 minutes past, so we should probably go ahead and get started. I don't think I have anything in the way of logistics. I kind of want to see a time lapse now of just everything that we've done.
All the lectures.
Yeah. So again, just to remind you, the target is 25 minutes for prepared material plus 5 minutes for feedback. Okay, so we're already a few minutes past. Welcome back, everybody. Thank you very much for coming back for part 2 of quantum field theory. Integral, right there. There you go. This is an integral, this is an integral, and now this is going to give me a new expression, which is still. I think this is the one where we had to roll up the sleeves and calculate.
I like central delta.
2 pi squared, 4 alpha EM squared over U squared times a similar. It's actually a term I stole from Evangelion.
I read it out. You are organized, actually.
Yeah, I guess so.
Same.
Thank you very much. That was a very kind gesture.
What's it like to learn math on Brilliant.org? Brilliant gets you
Terrible.
Okay. I think so or not.
Oh, someone not? Let's go. Sorry.
So unless you did it like super. I heard
Nice. Okay. Could be.
Okay.
Okay.
Okay, now we'll talk about quantum field theory in curved space. Some people here, me and Antonio and I think Andrew, we attend the GR class, but we know some of the things, but it's not that difficult. It's not applicable in general relativity. Okay, now I'll talk here. Yeah. Now the flat space compared to the curved space-time. We have the monitor shortly. Okay. Now we work from the beginning in our study on the flat space. If you remember, the metric tensor was 1, -1, -1, -1. Or this is the same metric tensor, and this is the flat space metric tensor in spherical coordinates. Now, in the work, what is the difference between the curved space-time and the flat space-time? For example, one of the differences is the volume element description in curved space is different than the one in the Euclidean flat space. The Ricci tensor is defined to describe this difference between the two spaces. As you see here, we have here a curved space, and here is the flat space. The volume element here is different than the same volume element in the flat space. The Ricci tensor, which is R, which is the second ranked tensor, it is can be found by multiplying the metric tensor multiplied by the Riemann tensor, which is R, which is the up to the fourth ranked tensor, and it's a combination of derivatives and Christoffel simples and the derivatives between the to convert from system to another system. The Riemann tensor, which plays the most important to describe the geometric properties of the space-time. If the components of this tensor are zeros, then this space-time is flat. And locally, not globally, for example, for accelerating system, the Riemann tensor is given by this, which is the derivatives with respect to of the metric tensors. The Christoffel simple is defined also by this relation, which is derivatives of metric tensors between the different spaces. Now, at the end, we have the Ricci scalar, which is simply the metric tensor multiplied by the Ricci tensor. This is just a number which give us a description about the curved space, what we work in. Now here, yes, for example, this is the Ricci.
Yeah, can you maybe move the small zoom box there? I think it's blocking your formula.
The bottom right.
This one?
Yeah.
Okay. Now, this is, for example, the Ricci tensor for a sphere. By applying this relation on it, we can find the Ricci scalar. This is just to show. Okay, we have some examples on the curved spaces or geometries. Now, one of the famous metric tensors is the Schwarzschild geometry metric, which describes the geometry about or around a massive object. It's almost flat geometric tensor, just like this one in spherical coordinates, but it contains the gravity and the mass properties inside its components. Also, we have not just the spherical symmetric metric tensor, we have many of these metric tensor, each one has its applications. Now in our study, or in my presentation here, we have this metric tensor which describes a flat space, but this space is expanding or contracting, which is the simplest model for the universe. which is a homogeneous and isotropic, and it's expanding or contracting. The line element, now all these quantities in spherical or the expressions in spherical coordinates, the line element is given by this relation. It's the same as the line element in flat space, but there's a time factors on the effect on the special part, which make it expand by the time or contract. And this is the metric tensor in spherical coordinates. Now here, depending on K here, our space is concave or which have negative or positive curvature, or if K here, which is omega here, if K is equal to 1, then our space is flat. We will not apply too much these things, but this is just to give an idea about the curved space. And this is the Ricci tensor again, okay, for our system today. Now, in general, our study in QFT, we passed or we solved the problem using 4 steps almost. At first, we need to find the Lagrange, then to find the equations of motion. Then we need to quantize our quantities using canonical quantization or the commutation relations and so on. Then we need to find or to characterize our quantum states. For example, we have the vacuum, the free vacuum, and the interactive vacuum. And we need to use the creation and annihilation operators. Then we have a physical interpretation. For example, we have measurements, we have masses, and so this is all in flat, homogeneous, isotropic space. But in curved space, we have some differences because our metric tensor is changed now. It is not, as we know, it's not 1 minus 1 minus 1 minus 1. We have another metric tensor now, which is this one in spherical coordinates. This will affect the calculations in general, but it will affect mostly the last two one. For example, the Lorentz symmetry is broken now, and the vacuum is not a unique state anymore. The concept of particles created or discussed in this point is different now. It's a bit more ambiguous. And some different explanations become more difficult. Okay, now we need to define our space. As I said from before, it's expanding flat space. It is not spherical, maybe it is a cylindrical. I should put maybe a expanded cylinder here. It is flat, but there's a curvature. Our space-time is given by d sigma spatial coordinates embedded in d sigma plus 1, which is the time coordinates that represent the expanding in the metric tensor. Now, this universe is defined by Robertson and Walker expand universe. And the metric tensor, this metric tensor now in Cartesian. As you see here, the time component, or this is the time component, this is a spatial component, and the spatial component lies under the effect of another coefficient affect its dimension. This metric, this line element goes under remapping, and we to make all the line elements. As we know, the flat space, this is eta, which is another time, just like t, and the effect of the expansion, a square of eta, effect on all of our space. Now these two representations is just like changing the scales. This one assumes that the universe started from negative infinity. But this one assumes that the zero time or our experiment is the origin. and the experiment starts from 0. Okay. Again, this is the Schwarzschild geometric metric tensor. This is the flat geometric tensor in the spherical coordinates. This is in Cartesian, as I said. Okay. What this gravitational field will affect in our calculations. But if you remember in quantum field theory 1, lecture 12, we define our Lagrangian by doing this process, and we have just the mass effect in the last formula here. We have half d phi minus half m squared phi squared. This is in a flat space. Now, if you look here, our study now doesn't contain any phi cubed or phi 4 to 4 fields, okay? But we will still in phi squared. Now, we just have added to this term here, we have another correction term, which is zeta multiplied by r. Now, in this case, I understand that the gravitational field is, or the gravitational correction is just an intrinsic property of the space-time, because we don't have any additional potentials. It looks like a correction also on our calculations. And this correction appears just at a place. We will see that at that moment we have a curvature, but before and after this curvature, we have a flat space again. Okay, now we need to derive again the Klein-Gordon like equation, or equation without like. As we know, then the Klein-Gordon equation will contain this term, which is zeta multiplied by r. Here we assume the universal constant equal to 1. R is the Ricci tensor, the Ricci scalar, sorry, for our curved space. Zeta here is a coupling constant. We will see that zeta will be 0, even 0, or 1/6, and there is no reason for that. Just the mathematical derivations show up in the 1/6. Okay. Now the solution for this, starting solving this problem in general. There is some approximations and considerations to solve this problem. At first, we have the time before and the time after. We have the space is flat, but at this moment, or the interaction moment, the space-time is curved. Before this interaction, in this region, the space is flat. And the function describe our space is f, small f, as a function of x and t. And the time is going to negative infinity. After the interaction, we have the same function, the same form of the function, but with it's capital F, which is a function of x and t. These two functions are small f and capital F are complete set, and we can write one of them in terms of the other one. At this moment, at the interaction moment, we have a continuity, and we have a potential, effective potential, and this effective potential is given by this. I didn't put it here, but we will see it. I don't know how it is derived, but it looks like m multiplied by m squared, which is our m, but we have the curvature effect, which is zeta minus 1/6. And 1/6 here, it appeared, I looked before on the derivations, it's just a number. There is no physical meaning for it. And if we need to apply the number operator, which is the creation annihilation operator, on the n function, which is small f, maybe this is that now if you look, now for small f and capital F, we have our commutation relations. And F has a coefficients in its definition. It's here. I'm looking for this. We have A for small f for the in function, and we have B's for the out function, a function. And they are given by this coefficient, which is alpha and beta. It connects the initial function with the final function. They are called the Bugloubal coefficients. And if we need to compute the creation and annihilation operator from the final function on the from the out function to on the in function, they will give us, if we apply this B dagger, it will give us beta squared summation over J. Now, if we have one of these betas not zero, then we have, it was before zero, and then it will not be zero. If we have one of them not zero, then we have a partial creation at this moment, just because we changed the representation of the functions using this effective potential. Now, to remind ourselves again, this is the Lagrangian in flat space. This is the metric tensor in flat space. This is the Klein-Gordon equation in flat space. This is our phi and momentum, which are the generalized coordinate and momentum. They are given by exponential, depending on spatial part. Also, there is a temporal part. But we are not in a flat space now. We are in different space, time. The Klein-Gordon equations will be like this. We have F for the in function and capital F for the out function. Now, let us just use the in function, and the out function will have almost the same image. This in function contains spatial part and the temporal part. Remember that eta is a time. Now, zeta psi of eta will be defined later. It will be an exponential of time also. Now, the process for this solution, this is the in function part, which is exponential in space, and psi in eta. Psi will be the solution of this equation. We can be solved from here by using some approximation. We'll see them now. We use this effective potential affected on our system. Now the approximations are the mass. We as always we consider the mass 0 to simplify things, and the static and the flat is space time before and after our interaction. Then psi of t or eta here is given by exponential again. This is for the in function, and the psi of eta for the out function is given by this one, which is, and alpha and beta again are related to the Bugloubal coefficients again. Now, solving these equations to find the number density, or the number density after the interaction, it will be given by this relation, which are the created particles, number of particles. It depends on beta of k, as we see from before here. And this is the integral form of that. We will see the solution of this now. And the energy density will be given by this also, which is just multiplied omega multiplied by beta squared. Now all of this interaction and this mathematical solution will take place just in now time, not before and not after. Now to solve that, we need to write this equation, which is looks like the wave equation with this effective potential. We need to write it in the integral form. using the same potential. But this potential now, we need to assume it as sufficiently small to just use the first term in the perturbation theory. And this will allow us to approximate to use the simplest functions, which is chi in, not chi out, to solve the problem. This will give us the alpha and beta coefficients, depending now, as we see, on the effective potential. Just the effective potential will determine these coefficients. For mass equal to 0, now the effective potential, if you remember, we have the we have the curvature constant inside it. Then the number density will be found by this integration, which is a coefficient multiplied by the curvature constant, which depends on time, because our interaction from passing from now to the future, the curvature depending on time. Before, the curvature was not 1, later is 1, now it is not 1 here at the interaction point. And the energy.
Just let me 5 minutes. 5 minutes remaining, okay? I'll make a bigger sign.
Okay, now this is the energy density also. Now for zeta here, it is 0 or 6, 1 over 6. If eta is 0, then we have number of particles created. But if zeta is equal to 1/6, then we will get back to our original flat space.
Oh, interesting.
Now, as an application of these formulas, I will pass because we don't have time, but if we need to apply some approximations and assume numbers to solve that. If we assume that the Ricci, that curvature constant is equal to 12h squared. H here is the energy transferred during the interaction, and h to -1 related to the time by the uncertainty principle. Then the time elapsed, and we need also to assume that the transition occurred during repeated time related to the energy also. The number of particles, it will depends now on the energy transferred in the system, which depends also on the time. Also, the energy density depending on the same things. If you see that now, the energy depends on the curvature. So everything depends on the geometry of the system. Okay, now, for example, just to compare the curvature effects in numbers on our space or on that assumed space. Here, rho v is the vacuum energy. Using that Planck's density and Einstein's equations. And if you know that the vacuum density is in rank 10 to 15 giga electron volts to 4 power, then then rho here calculated by our calculations or our show is up to the 10 to 11, which is much less than the vacuum, which is the flat vacuum energy. Okay. Yes, it is much less than this. The point is the curvature creation of the particle is negligible in general, because maybe we have effective potential much higher than this curvature in the space-time. But if the other effective potentials in the system or the space around this point are relatively small, then this effect will take place and will be affected in the particle creation in this point. For example, at the edge of the universe, there is a curve. There is no, there is no other forces. Then it will create particles, and this will be affected at the system at that time. Now, as an application of that is the Hawking radiation. Hawking did the same thing using I'll pass that for fast, and he just used the fast flat space, use harmonic, use spherical harmonics, and use the future, and the interaction take the now time, and he assumed that there's a ray passes through from passing through the null GDC through the, for example, this is a black hole or a massive object, which is a spherical symmetric, and passes it through. There is a changing. There's change appeared on the in function and appeared on the out function. And he found the alpha and beta. There are too much equations. I didn't go through them. And he found that the particle density follow this distribution, which is localized like the Planck's spectrum, with temperature equal to this, which depends on the mass of the black hole. And this called the how can temperature of the black hole, and this is the energy density, and which depends on n. N depends on m. M tell us about the geometry of the system, and there are three scenarios. What is the end of the black hole? How can go with this one? The final one is the totally the black hole will evaporate and the information will be lost at the end of the universe after too much long time. And thank you.
Okay, thank you very much, Mohammed. Your timing is pretty good. We've got time for a discussion. So let's start with any questions from students, either in the room or online.
Another thing, yes, I didn't say it about Hawking calculations. He used the Schwarzschild metric tensor, just like that. I didn't say that.
Yes, which you showed us before. Any questions?
So you have this metric tensor and the Ricci tensor. I've never taken any GR class or anything like that. So my impression was that the metric tensor would encode all of the information about the curvature of your space-time. Mm-hmm. So what is the Ricci tensor doing?
It's more simple way. Just, I'll show you. You see it here. Mm-hmm. So just the metric tensor multiplied by the Ricci tensor, which is just a number at this point. When you use it in the equation, you use a scalar. Okay. Where we can see it here. Here, you can use just a scalar. This scalar, if this scalar is equal to 1, then our space-time is flat. If this scalar is bigger than 1, then our space-time is the angle of the total the total summation of the angles is more than 180. If the curvature is less than 1, which is r, then we have the saddle shape, which is the negative.
Can you go one slide back, please, Mohammed? Everything that you said is correct. I just wanted to clarify something for Joe. These other tensors are just built out of derivatives of the metric tensor. So you're correct in your expectation that the metric encodes everything. Okay. Now the metric is a function of space-time, and these are the derivatives of the metric with respect to space-time.
Gotcha. You did an example using scalar fields. Like we didn't do any like scalar interactions like phi cubed or phi to the 4th theory. Is this just the scope of your presentation that's around scalar fields, or like is the scope of all space-time QFT dealing with scalars?
No, you can solve this problem using any one of these geometries.
Oh, okay.
But to simplify things, when this person, which is a cosmologist, he worked in cosmology with where is it? Robertson and Walker, they discussed the expanding universe.
Oh, okay.
So they put these suggestions that our space is flat in general, but we have some curvature at some points.
Can you do it for other kinds of particles? I think the question was, here you've done it for scalar
Yeah, sure,
particles.
sure.
Can you do it for spinors,
Sure,
vectors?
You remember when we deal with scalar particles in QFT, it's the simplest one.
But you can just propagate all this stuff for the other fields just the
Yeah.
same way.
Yeah, sure.
Wow. Okay.
I wonder if there's any extra complications of defining what a spinor is in curved spacetime. Are your U's and V's now screwed up because
There
of
is
the curved
discussions
spacetime?
on the edge of the black hole. If there's a, for example, electron and positron created at the edge, it is not simple like that. How can, I saw that many times on the resources.
Yeah.
It is not simple like that, just like that. There is a particle and antiparticle. One of them is attracted by the black hole and one of them will escape. It's not simple like that. There's calculations and the edge of this black hole is shrinking, okay? So if you need to say this for people who are not physicists, it's okay. But it is not okay for us.
Okay.
Even for us, it's difficult.
Any other questions from in the room or from online? No, I don't think I have any questions either. Anything that I thought I might want to ask, I think you've already answered it. I really like the nice demonstration that you can do sort of the boundary condition matching. Could you maybe go back, I think it was slide 10 or so, where you showed the past, the now, the future. That setup seemed very, yeah, this is the one. Yeah, so this reminds me very much of our scattering theory problems we did in 554, 555, where you've got some initial condition, some final condition. These ones are the free theories in flat space. We know the answers for something happens at t equals 0, and now you're doing the boundary condition matching, and you find that if you start off with the vacuum, you don't necessarily end with the vacuum. You can end with particles, and now you've calculated how many particles. So very nice. I thought that was a nice encapsulation of what we've been talking about. Okay, I think that's it. Any other questions before we move on to the next talk? Then let's thank Mohammed again. Thank you, sir.
Thank you.
We don't necessarily have any fixed order. If there are volunteers for who would like to go next, feel free. Otherwise, you can be voluntold.
I was just going to ask you.
Yeah.
Okay, great.
You want to go and I'm going to go before you.
That sounds good to me.
I'm going to run to the restroom really quick.
Yes. By the way, we've got some flexibility in the time. If anybody needs to request a break, just say something and we can take a few minutes. We're not super pressed for time.
I'll wait for the lunch.
That's what I was.
His name is Musa.
Okay. Thank you.
Which one?
What's his name?
That's Musa. I don't know the name.
You can see.
I don't want to.
Things we did the statues on top?
Huh? Yeah.
It's on the third, right?
Huh?
The third.
Yeah. Dr. Bauman said it should be this Musa. He requested the English translation for this.
Oh, okay. Just.
It looks so fancy. It's got a big PowerPoint presentation.
Very good.
Okay, are you seeing the new slides online, guys?
Yeah.
Yes.
Okay. And we can take a minute before we get started. The other thing that I wanted to do is switch the camera. Yes, thank you so much. The other thing I wanted to do is switch the camera so I can point it better at the speakers. So I'm going to turn on